Have you ever wondered if there are more than 3 dimensions in our universe? The concept of extra dimensions has fascinated scientists and the public alike for decades. In this video, we will explore the theories and practical applications of extra dimensions and how they could help us understand the fundamental nature of our universe. Hello and welcome to CVID, the channel that explores the fascinating world of science. In today's video, we will be discussing dimensions. Dimensions are different aspects of what we know as reality. The 3 dimensions that surround us on a daily basis are length, width, and depth. The 4th dimension is time, which governs the properties of all known substances at any point. Beyond these 4 dimensions, there are 6 more that are not immediately apparent to us, but can still be perceived as having a direct impact on the world and reality as we know it. Physical dimensions are qualities that describe the nature of a physical quantity such as length, mass, time, temperature, and electric charge. Physical dimensions are not numbers, but labels that indicate the units in which a quantity is measured. Physical dimensions are used to compare and combine physical quantities and ensure dimensional compatibility of equations and formulas. Physical dimensions are often denoted by symbols such as L for length, M for mass, and T for time. Physical dimensions are essential in physics and engineering, where they are used to describe and analyze the behavior of physical systems. Mathematical dimensions are properties of mathematical objects such as points, lines, planes, and spaces. Mathematical dimensions are defined as the minimum number of coordinates required to determine a point in a space. Mathematical dimensions are often represented by whole numbers, such as 0 for a point, 1 for a line, 2 for a plane, and 3 for a distance. Mathematical dimensions are used in geometry, topology, and other branches of mathematics to study the properties and relationships of mathematical objects. Mathematical dimensions can be higher than 3 and can be used to describe abstract spaces that do not correspond to physical reality. Physical and mathematical dimensions are related but distinct concepts. Physical dimensions are labels that describe physical quantities, while mathematical dimensions are properties of mathematical objects. Physical dimensions are essential in physics and engineering, while mathematical dimensions are used in geometry and other branches of mathematics. Dimensional analysis is a method used in science to analyze and convert physical quantities and their measurement units. It is often used to convert units of measurement from one system to another. For example, it can be used to convert meters to feet or grams to pounds. This is done by multiplying the original value by the conversion factor, which cancels the original units and substitutes the desired units. Dimensional analysis can also be used to check the correctness of equations and formulas. If the dimensions of the expressions on both sides of the equation do not match, the equation is not valid. This can help identify errors in calculations and ensure that the results are physically meaningful. Dimensional analysis can simplify complex calculations by reducing them to a series of simple unit transformations. This can make calculations easier and reduce the risk of error. In conclusion, dimensions are an essential concept in science and mathematics. They help us understand the nature of physical quantities and mathematical objects. Physical dimensions are used to describe and analyze the behavior of physical systems, while mathematical dimensions are used to study the properties and relationships of mathematical objects. Dimensional analysis is a powerful tool widely used in physics, chemistry, engineering, and other sciences to analyze and convert physical quantities and their measurement units. In physics and mathematics, a dimension is informally defined as the minimum number of coordinates needed to specify any point within a mathematical space or object. In other words, it is a parameter or measure of spatial characteristics of an object, such as length, width, and height. Here are some examples of how dimensions are used in physics and cosmology. 1. Describing physical quantities. In physics, the dimension of a physical quantity is the expression of the class of physical unit that such a quantity is measured against. For example, length L is the dimension for measurements expressed in units of length, such as meters, nautical miles, or light years. Time t is another example of a dimension, which is expressed in units such as seconds or hours. 2. Describing the universe. In cosmology, dimensions are used to describe the different facets of what we perceive to be reality. We are immediately aware of the three dimensions that surround us on a daily basis, those that define the length, width, and depth of all objects in our universes. Beyond these three lie the seven dimensions which are not immediately apparent to us, but which can still be perceived as having a direct effect on the universe and reality as we know it. Scientists believe that the fourth dimension is time, which governs the properties of all known matter at any given point. 3. Deriving equations. In physics, dimensions are used to derive equations and relationships between physical quantities. By analyzing the dimensions of the quantities involved in a phenomenon, scientists can determine how they are related and derive equations that describe their behavior. 4. Simplifying calculations. In physics, dimensions can simplify complex calculations by reducing them to a series of simple unit conversions. This can make it easier to perform calculations and reduce the risk of errors. Overall, dimensions are essential in physics and cosmology, where they are used to describe and analyze the behavior of physical systems and the universe as a whole. Now let's talk about compactified dimensions in cosmology. A compactified dimension refers to a spatial dimension that is curled up or compacted into a very small size, making it unobservable at macroscopic scales. Here are some key points to understand the concept of a compactified dimension in cosmology. Compactification is a process of changing a theory with respect to one of its space-time dimensions, so that instead of having a theory with this dimension being infinite, one changes the theory so that this dimension has a finite length, and may also be periodic. In string theory, compactification is a generalization of Kaluza-Klein theory. It tries to reconcile the gap between the conception of our universe based on its 4 observable dimensions with the 10, 11, or 26 dimensions which theoretical models of string theory require. The idea of compactified dimensions is used to explain the existence of extra dimensions in the universe, which are not directly observable at macroscopic scales. These extra dimensions are thought to be curled up or compacted into a very small size, making them unobservable. Compactified dimensions play an important role in the study of quantum gravity and the unification of all fundamental forces in the universe. They are also used to explain the properties of black holes and the behavior of particles at high energies. The concept of compactified dimensions is still a subject of active research in cosmology and theoretical physics, and many questions about the nature of these dimensions remain unanswered. Overall, the concept of compactified dimensions is a key idea in cosmology and theoretical physics, which helps to explain the existence of extra dimensions in the universe and the behavior of particles at high energies. Compactification of dimensions can have significant effects on the behavior of particles in the universe. Here are some ways in which compactification of dimensions affects the behavior of particles. 1. Changes in particle properties. When a dimension is compactified, the properties of particles that move in that dimension can change. For example, the mass of a particle can depend on the size of the compactified dimension, and the wave function of a particle can be modified by the topology of the compactified dimension. 2. Changes in particle interactions. Compactification of dimensions can also affect the way that particles interact with each other. For example, the strength of the electromagnetic force can depend on the size of the compactified dimension, and the number of particle species that exist can depend on the topology of the compactified dimension. 3. Changes in the spectrum of particles. Compactification of dimensions can also affect the spectrum of particles that exist in the universe. For example, in string theory, compactification of the extra dimensions can lead to the prediction of new particles that are not observed in our four-dimensional world. 4. Changes in the geometry of spacetime. Compactification of dimensions can also affect the geometry of spacetime. For example, in some models of cosmology, the universe is assumed to have compactified dimensions, which can lead to a variety of interesting phenomena such as the formation of cosmic strings and the production of gravitational waves. Overall, compactification of dimensions is an important concept in cosmology and theoretical physics, which can have significant effects on the behavior of particles in the universe. By understanding the effects of compactification, scientists can gain insights into the fundamental nature of the universe and the behavior of its constituent particles. Two dimensions refer to motion or quantities that take place along two different directions at the same time and require at least two coordinates to be described. Here are some examples of how two dimensions are used in physics and cosmology. Motion in two dimensions. In physics, motion in two dimensions is a common concept used to describe the motion of objects in two different directions. Examples of this type of motion include the motion of a projectile, the motion of a car on a curved road, and the motion of a planet around a star. Vector addition and subtraction. In physics, vectors are quantities that have both magnitude and direction. In two dimensions, vectors can be added and subtracted using graphical methods to determine the displacement of moving objects. Examples of vectors in two dimensions include displacement, velocity, acceleration, and force. Reference frames. In physics and astronomy, a reference frame is an abstract coordinate system whose origin, orientation, and scale are specified by a set of reference points. For two dimensions, 3 reference points are sufficient to fully define a reference frame. Reference frames are used to describe the motion of objects relative to a fixed point in space. Lorentz transformation. In cosmology, the Lorentz transformation is a mathematical formula used to describe the relationship between space and time in special relativity. The transformation involves 4 dimensions, 3 of which correspond to space and 1 to time. The transformation is used to describe the behavior of particles at high speeds and the properties of black holes. In physics, position and time coordinates are used to describe the motion of objects in two-dimensional space. The position of an object is described by 2 coordinates, usually denoted as x and y. These coordinates can be used to specify the location of an object in a two-dimensional plane. The position of an object can be represented by a position vector, which is a vector that points from the origin of the coordinate system to the object's location. Time is a scalar quantity that represents the duration of the motion. Time coordinates can be used to describe the motion of an object over time. The position of an object at a given time can be represented by a position vector that depends on the time. In two-dimensional motion, the motion of an object can be described using equations that relate the position of the object to time. For example, the position of an object at a given time can be described by this equation, where x0 is the initial position, v0x is the initial velocity in the x direction, a is the acceleration, and t is the time. Vectors can be added and subtracted using graphical methods to determine the displacement of moving objects. The displacement of an object can be represented by a vector that points from the initial position to the final position. Overall, position and time coordinates are essential in describing the motion of objects in two-dimensional space. By understanding the properties of position and time coordinates, scientists can gain insights into the fundamental nature of the universe and the behavior of its constituent particles. In physics and cosmology, 3 dimensions are crucial for understanding the behavior of particles, the geometry of space-time, and the properties of the universe. Let's explore the concept of 3 dimensions and how they are used in various fields. In physics, 3 dimensions refer to motion or quantities that take place along 3 different directions at the same time and require at least 3 coordinates to be described. Here are some examples of how 3 dimensions are used in physics and cosmology. 1. Describing physical space. In classical physics, 3 dimensions of physical space are described as up/down, left/right, and forward/backward. These dimensions are used to describe the position and motion of objects in space. In addition to these 3 dimensions, time is considered as the 4th dimension in physics. 2. Describing the universe. In cosmology, 3 dimensions are used to describe the spatial dimensions of the universe. The universe is thought to be expanding in all 3 dimensions, and the properties of the universe are described using equations that involve these 3 dimensions. 3. Vector addition and subtraction. In physics, vectors are quantities that have both magnitude and direction. In 3 dimensions, vectors can be added and subtracted using graphical methods to determine the displacement of moving objects. Examples of vectors in 3 dimensions include displacement, velocity, acceleration, and force. 4. Describing the behavior of particles. In particle physics, 3 dimensions are used to describe the behavior of particles. The properties of particles, such as their mass, charge, and spin, are described using equations that involve 3 dimensions of space and 1 dimension of time. 5. String theory. In string theory, which is a theoretical framework that attempts to reconcile quantum mechanics and general relativity, the universe is described as having 10 dimensions, with 6 of these dimensions being compactified or curled up. These extra dimensions are thought to be responsible for the properties of particles and the behavior of the universe at high energies. Overall, 3 dimensions are an important concept in physics and cosmology, which are used to describe the behavior of particles, the geometry of spacetime, and the properties of the universe. By understanding the properties of 3-dimensional systems, scientists can gain insights into the fundamental nature of the universe and the behavior of its constituent particles. Spacetime is a concept in physics that combines the 3 dimensions of space and the 1 dimension of time into a single 4-dimensional continuum. This concept was first proposed by the mathematician Hermann Minkowski in 1908 as a way to reformulate Albert Einstein's special theory of relativity. Spacetime is a mathematical model that is used to describe the behavior of objects in the universe, and it is an essential concept in modern physics and cosmology. Here are some key points to understand the concept of spacetime and how it relates to the dimensions of space. 4 dimensions. Spacetime is a 4-dimensional continuum that combines the 3 dimensions of space with the 4th dimension of time. In ordinary space, a position is specified by 3 numbers, known as dimensions. In the Cartesian coordinate system, these are called x, y, and z. A position in spacetime is called an event and requires 4 numbers to be specified, the 3-dimensional location in space, plus the position in time. Spacetime continuum. The spacetime continuum is a concept that recognizes the union of space and time. According to Einstein's theory of relativity, space and time are not separate phenomena, but are interwoven into a single continuum that spans multiple dimensions. The spacetime continuum consists of 4 dimensions, the 3 dimensions of space plus the 4th dimension of time. Geometric qualities. The concept of spacetime emphasizes the geometric qualities of space and time. Spacetime diagrams can be used to visualize relativistic effects, such as why different observers perceive differently where and when events occur. Unification of forces. The concept of spacetime is an essential concept in the unification of the fundamental forces of nature. In some theories, the extra dimensions of spacetime are used to unify gravity with the other fundamental forces, such as electromagnetism and the strong and weak nuclear forces. Overall, the concept of spacetime is an essential concept in modern physics and cosmology. By understanding the properties of spacetime and its relationship to the dimensions of space, scientists can gain insights into the fundamental nature of the universe and the behavior of its constituent particles. String theory and M-theory are both fundamental theories in physics that aim to provide a unified theory of the universe. String theory attempts to reconcile quantum mechanics and general relativity. The fundamental building blocks of the universe are tiny, 1-dimensional strings. String theory requires the existence of extra dimensions beyond the 3 spatial dimensions and 1 time dimension that we observe. In string theory, spacetime is 10-dimensional 9 spatial dimensions and 1 time dimension. String theory has 5 consistent versions, known as Type 1, Type IIA, Type IIB, heterotic SO32, and heterotic E8x E8. M-theory attempts to unify all consistent versions of string theory. M-theory requires the existence of an 11th dimension beyond the 10 dimensions of string theory. M-theory is like an Uber theory of strings, showing how all 5 string theories are really just small corners of a much larger, and much more mysterious, theory. M-theory is still a work in progress, and much is still unknown about it. One of the main goals of string theory and M-theory is to unify the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. These theories suggest that all of these forces are different manifestations of a single underlying force. Both string theory and M-theory require the existence of extra dimensions beyond the 3 spatial dimensions and 1 time dimension that we observe. In string theory, spacetime is 10-dimensional 9 spatial dimensions and 1 time dimension, while in M-theory it is 11-dimensional 10 spatial dimensions and 1 time dimension. These extra dimensions are necessary to make the mathematical equations of these theories consistent. Supersymmetry is a mathematical relation that exists in certain physical theories between a class of particles called bosons and a class of particles called fermions. In theories with supersymmetry, each boson has a counterpart which is a fermion, and vice versa. Supersymmetry is important because it provides a way to unify the fundamental forces of nature. In string theory, supersymmetry is a necessary condition for the consistency of the theory. M-theory requires the existence of an 11th dimension beyond the 10 dimensions of string theory, and supersymmetry is used to ensure the consistency of the theory in this extra dimension. String theory and M-theory are important theories in modern physics that attempt to provide a unified theory of the universe. By studying the properties of these theories, scientists hope to gain insights into the fundamental nature of the universe and the behavior of its constituent particles. Virtual reality systems use spatial dimensions to create immersive experiences for users. By simulating 3-dimensional spaces, virtual reality systems can create the illusion of being in a different environment. For example, virtual reality systems can be used for digital archaeological exhibitions, or to create spaces that are responsive to structures independent from 3-dimensional spatial constraints. Computer graphics use spatial dimensions to create 3-dimensional images and animations. By using 3-dimensional models, computer graphics can create realistic and detailed images that can be viewed from different angles. For example, 3D computer images are fundamental to modern industries such as architecture, engineering, and film and entertainment. Computer graphics can also be used for education, such as teaching the basics of computer graphics and virtual reality. Augmented reality systems use spatial dimensions to overlay digital information onto the real world. By using spatial tracking and sensing, augmented reality systems can determine the position and orientation of the user in space. For example, augmented reality systems can be used to measure the focal distance of the virtual image in an augmented reality or virtual reality device. Creating realistic 3D environments requires a combination of techniques, including polygonal modeling, sculpting, lighting, texturing, and LOD. By using these techniques, computer graphics artists can create immersive and believable scenes that can be used in a variety of practical applications. In conclusion, spatial dimensions are an essential concept in computer graphics and virtual reality. By using spatial dimensions, these technologies can create realistic and immersive experiences for users, and can be used in a variety of practical applications. The dimensions of space are a fascinating and essential concept in physics and cosmology. Space and time are simultaneous phenomena and together form the fabric of the universe known as spacetime. René Descartes envisioned there to be 3 dimensions of space, with a totally separate dimension of time that together specify an object's position in physical space. Albert Einstein introduced the concept of 4-dimensional spacetime, which merged space and time into spacetime and helped introduce a new framework. The theoretical framework of superstring theory posits that the universe exists in 10 different dimensions. Beyond the 3 dimensions that we are immediately aware of, there are 7 dimensions which are not immediately apparent to us, but which can still be perceived as having a direct effect on the universe and reality as we know it. The 4th dimension is time, which governs the properties of all known matter at any given point. Knowing an object's position in time is essential to plotting its position in the universe. From the direct evidence we have, there are 3 spatial dimensions and 1 time dimension, and no more are required to solve any problems or explain any phenomenon we've ever observed. In three spatial dimensions, signals like the intensity of sound, the flux of light, even the strength of the gravitational and electromagnetic forces, they all fall off as 1 over the distance squared, spreading out like the surface of a sphere. The number of dimensions varies, but the purpose behind extra dimensions is to find ways of unifying the known laws of the universe, which theoretical physicists have been trying to do for about a century. String theory intriguingly suggests that 6 more dimensions exist, but are somehow hidden from our senses. They could be all around us, but curled up to be so tiny that we cannot detect them. In conclusion, virtual reality has shown great potential in education, particularly in enhancing spatial perception and providing immersive learning experiences. Furthermore, some theories in physics, such as string theory, suggest the existence of additional dimensions beyond the 3 spatial dimensions and 1 time dimension that we observe, which could be related to the concept of virtual reality. As we continue to explore the possibilities of virtual reality, we may gain new insights into the nature of our universe and our place within it. Thank you for watching CVID, and we hope to see you again soon. Like this video if you enjoyed it. Let me know what you think in the comments below.